Most stars leave something behind when they die. A star like our Sun will swell into a red giant, shed its outer layers, and leave a white dwarf at its center. A dense, cooling remnant that will persist for trillions of years, slowly fading into the dark. A more massive star will collapse its core into a neutron star, an object the size of a city but containing more mass than the Sun, spinning hundreds of times per second, radiating energy from magnetic poles in beams of radiation that sweep through space like lighthouse beams. The most massive stars of all will collapse their cores into black holes, regions of spacetime so warped by gravity that nothing, not even light, can escape. In every case, something remains, a remnant, a marker, some dense, small, extraordinary object that tells the universe that a star was here, that it lived and burned and died, and that the physics of matter under extreme conditions produced this specific artifact from this specific death. In every case, except one, there is a type of stellar death so violent, so complete, so total in its destruction, that nothing remains. Not a white dwarf, not a neutron star, not a black hole, not even a dense core of heavy elements cooling in the debris. Nothing. The star that undergoes this death does not leave a remnant. It does not collapse into something new. It does not transfer its energy into a compact object that carries on in some form. It simply ceases to exist. Every atom that made it up, every particle of the matter assembled over millions of years in a stellar core, is flung outward at a fraction of the speed of light, scattered into the surrounding space, never to reconvene. The star that was there is not there anymore, not transformed, not compressed, gone. This is the parent stability supernova, the most violent type of stellar explosion in the universe, an event that was theorized for decades, sought with increasingly powerful telescopes, and confirmed only recently in a way that changes what we understand about the most massive stars ever to exist. And in May of 2026, astronomers published the most compelling evidence yet that one had been directly observed. A star designated SN 2023 VBW, a blue supergiant that was already one of the most massive objects in its galaxy, destroyed itself so completely that the debris it left contained between 170 and 350 times the mass of the Sun, with no compact remnant anywhere in the expanding cloud. Just light, just energy, just the dispersed remains of a star that ceased to exist. This is that story. Before you can understand why a parent stability supernova is different from every other type of stellar death, you need to understand something about the physics of stars in general, about the fundamental tension that every star lives with from the moment it ignites until the moment it dies. A star is, at its most basic, a balance between two forces. Gravity pulls inward. The weight of all the star's mass presses down toward the center, trying to compress everything into the smallest possible volume. This gravity is immense. In a star like the Sun, the pressure at the center is estimated at 250 billion times the atmospheric pressure at Earth's surface. If gravity were the only force acting, a star would collapse in seconds. It does not collapse because of the outward pressure produced by the energy generated in the star's core. Nuclear fusion, the process by which lighter atomic nuclei are fused together into heavier ones, releasing energy, produces photons and heat that exert an outward pressure on the surrounding material. This pressure, called radiation pressure and thermal pressure, pushes outward against gravity. As long as the fusion continues, as long as the fuel holds out, the outward pressure balances gravity and the star is stable. This balance is called hydrostatic equilibrium, and it is the condition that defines a star. When the fuel runs out, the balance ends. Gravity wins. The core collapses. What happens next depends entirely on the mass of the core, on how much material has accumulated, how hot the core has become, what fusion reactions were possible during the star's lifetime, and what physical processes can provide the pressure needed to halt or at least resist the collapse. For most stars, including our Sun, the collapse is halted by electron degeneracy pressure. Electrons, as quantum particles, obey the Pauli exclusion principle, which prevents two electrons from occupying the same quantum state. As the core is compressed to extreme densities, This quantum mechanical resistance provides enough pressure to stop the collapse. The result is a white dwarf, an object supported not by fusion but by the fundamental quantum properties of electrons. For more massive stars, even electron degeneracy pressure is not enough. The core collapses further, the electrons and protons are squeezed together to form neutrons, and neutron degeneracy pressure, the same Pauli exclusion principle applied to neutrons, halts the collapse. The result is a neutron star. For the most massive stellar cores of all, even neutron degeneracy pressure fails. The collapse continues through the neutron star to a point of no return, a singularity, and a black hole is formed. Each of these outcomes involves a remnant, something left behind, something that formed from the matter of the original star. The parent stability supernova is different because it involves a mechanism that does not allow the collapse to produce a remnant. It involves a process so violent, triggered by physics so extreme, that the entire star, core included, is blown apart before any remnant can form. Understanding why requires understanding what happens inside a star more massive than any star currently in the Milky Way. Let's build up to the physics slowly, because it is genuinely extraordinary and deserves to be understood rather than simply stated. In a normal massive star, the late stages of nuclear burning involve the fusion of progressively heavier elements in the core. After hydrogen is exhausted, helium burns. After helium, carbon. After carbon, neon, then oxygen, then silicon. Each stage is shorter and more energetically demanding than the last. Silicon burning, the final stage, produces iron. And iron, as we have discussed, cannot be fused to release energy. The iron core accumulates, grows, and eventually becomes so massive that the thermal and radiation pressure in the surrounding layers cannot support it. Gravity wins. The collapse begins. In a very massive star, one with significantly more mass than typical supergiants, something different happens before the iron core forms. Something that involves quantum mechanics, relativity, and the production of matter from pure energy in a way that fundamentally destabilizes the star from within. At the extreme temperatures produced in the cores of the most massive stars, temperatures exceeding 5 billion degrees, the photons produced by nuclear burning have enough energy to do something normally impossible. They can spontaneously convert into pairs of particles, specifically an electron and its antiparticle, a positron. This process, pair production, is a direct consequence of Einstein's famous equation relating energy and mass. Photons with sufficient energy can materialize as particle-antiparticle pairs. In ordinary stellar environments, this does not happen at significant rates because the temperatures are not high enough. But in the cores of the most massive stars, the temperatures reach the threshold where pair production becomes a significant process. And pair production in a stellar core is catastrophic. Here is why. The radiation pressure that helps support the star against gravity comes from photons, from the electromagnetic radiation produced by nuclear burning. When those photons are converted into electron-positron pairs, they are removed from the radiation field. The radiation pressure drops. Not catastrophically, not immediately, but enough to slightly reduce the outward pressure supporting the core against gravity. Enough for the core to contract slightly. And as the core contracts, it heats. And as it heats, more pair production occurs, which reduces radiation pressure further, which causes more contraction, which causes more heating, a runaway process, a catastrophic positive feedback loop that the star has no mechanism to stop. The core begins to collapse. But unlike a conventional core collapse, which proceeds to a neutron star or black hole, in the most massive stars, the collapse is so rapid and generates so much heat so quickly that something extraordinary happens before a compact remnant can form. The collapsing core ignites explosive thermonuclear burning. The oxygen and silicon in the core detonate, not burn steadily as in the normal stellar fusion process, but detonate like a thermonuclear explosion of almost incomprehensible scale. The energy released in this explosion is so enormous that it reverses the collapse entirely. Not slows it, reverses it. The shock wave produced by the thermonuclear detonation blows the entire star, core and all, outward at velocities measured in thousands of kilometers per second. Everything, every layer, every atom, outward. There is no remnant because the thermonuclear energy is so large that it exceeds the gravitational binding energy of the entire star. The explosion does not just overcome the collapse of the core, it overcomes the gravity holding the whole star together. The star is completely unbound. Every piece of it flies outward, never to return. The parent stability supernova is not a core collapse. It is the complete thermonuclear destruction of an entire star. And the energy it releases is staggering. Let's put numbers to this. A typical core collapse supernova, the standard death of a massive star, releases approximately 10 to the power of 44 joules of energy, most of it in neutrinos. The optical luminosity, the amount of energy released as visible light, is roughly 10 to the power of 43 joules. A parent stability supernova releases approximately 10 to the power of 44 to 10 to the power of 45 joules, but with a crucial difference. Because there is no collapse to a neutron star and therefore no flood of neutrinos carrying away most of the energy, the fraction of the total energy released as light and kinetic energy of the ejecta is much higher. A parent stability supernova can convert 10 times or more of its total energy into visible radiation compared to a conventional supernova. The result is that a parent stability supernova can be extraordinarily bright, potentially among the brightest stellar explosions ever seen. Some parent stability supernova candidates have been observed at peak luminosities more than 100 times brighter than a typical supernova. Events so bright that they would outshine every other star in their host galaxy combined. In the astronomical literature, these extraordinarily bright explosions are called superluminous supernovae. Not all superluminous supernovae are parent stability events. Other mechanisms can produce extreme luminosity. But the most luminous, longest-lasting, and most energetic superluminous supernovae are consistent with parent stability events, and identifying the parent stability cases has been a major goal of observational astronomy for years. The ejecta mass is another distinguishing feature. A conventional core collapse supernova ejects the outer layers of the star, typically 5 to 15 solar masses of material, while leaving the core as a compact remnant. Parent stability supernova ejects everything. The entire star, tens to hundreds of solar masses of material, depending on the progenitor's initial mass, blown outward at velocities of up to 20,000 kilometers per second. SN 2023 VBW, the event observed in 2023 and analyzed over subsequent years, had an estimated ejecta mass of 170 to 350 solar masses. That is the entire star. That is between 170 and 350 times the mass of the Sun, distributed across an expanding cloud of debris, with nothing left at the center. An explosion that scattered between 170 and 350 suns worth of material into the surrounding space in a matter of seconds. Let's talk about what kind of star can produce this. The parent stability mechanism operates only in a specific mass range. Stars below a certain mass threshold, roughly 100 to 130 solar masses, depending on composition, do not reach the core temperatures required to trigger significant pair production. Their deaths follow the conventional path to neutron stars or black holes. Stars above a certain mass threshold, roughly 260 solar masses and above, undergo a different version of the instability. In these extreme cases, the thermonuclear energy released during the collapse is not enough to completely unbind the star. The outer layers are blown off, but the core continues to collapse to a black hole. This variant, sometimes called the pulsational parent stability supernova or direct collapse, also destroys much of the star but can leave a very massive black hole behind. The parent stability supernovae that leave nothing, the complete total destruction events, occur in the intermediate mass range, approximately 130 to 260 solar masses. Stars in this range reach high enough temperatures for significant pair production, collapse violently enough to trigger a thermonuclear detonation, and have cores massive enough that the detonation energy exceeds the gravitational binding energy of the entire system. In today's universe, stars this massive are extraordinarily rare. The most massive stars currently known, objects like our 136A1 in the Large Magellanic Cloud, estimated at roughly 200 to 300 solar masses, are at or above the threshold. They exist in specific environments: dense stellar clusters in metal-poor dwarf galaxies, regions where the conditions for forming extremely massive stars are present. Their rarity is partly a consequence of their mass. Very massive stars are not formed easily. Star formation generally produces many more low-mass stars than high-mass ones. The stellar initial mass function decreases steeply with increasing mass. Stars of 150 solar masses are orders of magnitude rarer than stars of 1 solar mass, and their rarity is partly a consequence of their brevity. Very massive stars live extraordinarily short lives. A star of 150 solar masses burns through its hydrogen fuel in perhaps 2 to 3 million years, a geological eye blink, less than 1,000th of the Sun's expected main sequence lifetime. They form, burn, and die in a fraction of the time that the Sun has been quietly fusing hydrogen. So parent stability supernovae are rare not only because the stars that produce them are rare, but because those stars die quickly and leave nothing behind. No neutron star to spin down and radiate. No black hole to accrete and produce jets. No white dwarf to cool. Just a cloud of expanding debris that thins over centuries. In the early universe, the first billion years, when the conditions were different, when the gas was less enriched with heavy elements, when the first stars were forming from pristine hydrogen and helium, parent stability supernovae may have been far more common. The first generation of stars, forming without the cooling influence of metals in the gas, may have been predominantly very massive. Populations of stars that lived and died in parent stability explosions before any instrument existed to observe them. Their chemical legacy, scattered across the early universe, may be detectable today in the oldest, most metal-poor stars, still living stars whose atmospheres carry the specific chemical fingerprints of parent stability ejecta. This connection between the parent stability supernova and the first stars in the universe is one of the deepest reasons astronomers care so much about finding these events. Now let's talk about SN 2023 VBW specifically, because this is the most compelling individual event ever observed and the one that anchors the current scientific conversation. The designation tells you when it was discovered. SN 2023 VBW, Supernova 2023, the 4,348th transient event cataloged in 2023. It was discovered in late 2023 in a host galaxy with relatively low metallicity, a galaxy where the gas has been less enriched with heavy elements than the Milky Way, which is exactly the kind of environment where very massive stars are more likely to form. The initial photometric data, the brightness measurements across different wavelengths, flagged it as unusual immediately. It was bright, extremely bright, and it was slow. Conventional supernovae rise to peak brightness in days to a few weeks and then decline on similar timescales. SN 2023 VBW rose over a much longer period, suggesting an enormous amount of material in the ejecta that took longer to heat and illuminate. The team that ultimately published the parent stability analysis, led by Daiichi Hiramatsu and collaborators, published in 2026, obtained spectroscopic data over an extended observing campaign. They tracked the supernova's light curve, its spectral evolution, and the velocity of the ejecta over months of observation. The spectral data told the story. The expansion velocity of the ejecta was high, consistent with the enormous energy released in a parent stability explosion. The spectral features were consistent with a massive blue supergiant progenitor. The estimated ejecta mass of 170 to 350 solar masses was the critical number. No conventional core collapse supernova ejects this much material. The numbers only make sense if the entire star was destroyed, and the analysis found no evidence of a compact remnant. In a conventional supernova, certain spectral features and emission patterns reveal the presence of the compact object at the center, heating of the surrounding nebula by the neutron star's rotation, for instance, or characteristic X-ray emission. In SN 2023 VBW, these signatures were absent. Nothing at the center, nothing left behind. 170 to 350 solar masses of stellar material scattered into the surrounding space, still expanding, still cooling, still dispersing. The paper described SN 2023 VBW as the most compelling candidate for a genuine parent stability supernova yet observed. Not the first candidate, several earlier events had been proposed, but the one with the most consistent set of observational properties, the most detailed data, and the fewest alternative explanations. It is not, by the strict standards of scientific proof, a confirmed parent stability supernova. The authors are careful to use the language of evidence and consistency rather than certainty. Other explanations, a particularly massive conventional supernova, an interaction between the ejecta and a dense surrounding shell of previously ejected material, cannot be completely ruled out from current data. But the weight of the evidence points clearly. SN 2023 VBW almost certainly destroyed itself completely. Let's step back and think about what it means for a star to leave nothing behind. In ordinary human experience, things that exist leave traces. A fire leaves ash. A wave leaves wet sand. A storm leaves debris. The physical world is conservative. Matter and energy are not created or destroyed, only transformed. Whatever was there before becomes something else, but it does not vanish. The parent stability supernova does not vanish in the sense of violating conservation laws. The matter that made the star still exists. The energy that was locked in its nuclear fuel has been released and is dispersing into the universe. Conservation of energy and mass energy are not violated. But the star, as a gravitationally bound entity, as a specific object occupying a specific location in space, ceases to exist. Not transformed into something new at that location. Dispersed, scattered. The atoms that made it are gone, flying outward at thousands of kilometers per second, heading in all directions, never to reconvene under any realistic set of physical conditions. In 100,000 years, the expanding cloud of debris from a parent stability supernova will be a vast, thin, dispersed structure hundreds of light years across, its density negligible compared to the surrounding interstellar medium. In 1,000,000 years, it will have mixed with that medium entirely, indistinguishable from the surrounding gas and dust. In 1,000,000,000 years, the atoms that made the star will have cycled through other stars, other planets, other processes. The star is not there, not in any form that preserves its identity as the object it was. This is a different kind of ending from anything else the universe produces in the deaths of stars. A neutron star spins for billions of years. A black hole persists, potentially, for longer than the current age of the universe many times over. Even a cooling white dwarf will be recognizable as the remnant of a specific stellar death for trillions of years. The parent stability supernova leaves nothing to mark its location. No tombstone, no remnant, just a brief, extraordinary flash of light, the most luminous individual event in the local universe, and then nothing. The space where the star was is empty space. The matter that made it is everywhere and nowhere. It is as complete a disappearance as the physical laws of the universe permit. Now let's go to the early universe, because the parent stability supernova is not just a rare event in the modern universe. It may have been one of the most important events in the history of the cosmos, a dominant mode of stellar death in the first few 100 million years of time. The first stars, population 3 stars, as they are called in astronomical terminology, the very first generation of stars to ignite in the universe, formed from gas that was almost entirely hydrogen and helium. The primordial gas produced in the Big Bang. No carbon, no oxygen, no iron, no heavy elements at all beyond trace amounts of lithium. This matters for star formation because heavy elements play a crucial role in the cooling of gas clouds. When a gas cloud cools, it loses energy and contracts under gravity, eventually becoming dense enough to ignite nuclear fusion. The cooling is mediated by the emission of radiation, and heavy elements, particularly carbon and oxygen, are extraordinarily efficient radiators. They cool gas rapidly. Hydrogen and helium, by contrast, are poor radiators. A gas cloud made entirely of hydrogen and helium cools slowly. It has to contract further, become denser and hotter, before it collapses to form stars. And a hotter, denser collapsing cloud tends to fragment less than a cooler one, It does not break up into many small clumps as readily as a metal-enriched cloud would. Instead, it tends to form fewer, more massive objects. The theoretical expectation, supported by increasingly sophisticated simulations, is that population 3 stars were predominantly very massive, perhaps the most massive stars that ever existed. Typical masses of 100 solar masses or more, a significant fraction perhaps exceeding 200 solar masses. A significant fraction, in other words, that would die as parent stability supernovae. The first generation of stars in the universe may have been dominated by objects that would leave no remnant, that would burn hot and fast for a few million years and then destroy themselves completely, scattering their nuclear products, the oxygen, silicon, and heavier elements forged in their cores, into the surrounding gas. This first enrichment of the universe with heavy elements, the chemical legacy of parent stability supernovae from population 3 stars, is encoded in the oldest surviving stars we can observe today. Stars that formed in the second generation, from gas that had been enriched by the deaths of the first stars. Their atmospheres carry a chemical fingerprint of the nucleosynthesis that happened in the first stellar generation. And parent stability nucleosynthesis produces a specific, distinctive chemical fingerprint. Because no neutron star is formed, there is no neutron capture synthesis of heavy elements above iron. The ejecta is dominated by lighter elements: oxygen, neon, magnesium, silicon, sulfur, argon, calcium, titanium, and nickel-56, which decays to iron-56. And specifically, there is a characteristic pattern in the ratio of elements produced. Parent stability supernovae produce an odd-even pattern in elemental abundances, with even-numbered elements relatively abundant and odd-numbered elements relatively depleted. In 2023, a team of astronomers examining the chemical composition of a very ancient, very metal-poor star named Lamos J1010 plus 2358 found exactly this pattern. An unusual ratio of elements with specific features, extremely low sodium and cobalt abundances, a specific iron abundance, and an overall pattern consistent with enrichment from a parent stability supernova of a star approximately 260 solar masses. The chemical ghost of a star that died more than 13 billion years ago, its signature preserved in the atmosphere of a second-generation star that has been floating in the Milky Way's halo ever since. The first star that ever underwent a parent stability supernova probably did so within the first few 100 million years of the universe's existence. We cannot observe it directly, but its ashes are still here, encoded in the chemistry of ancient stars, readable with sufficiently precise instruments. The past is not gone. It is written in the stars that survived it. Let's talk about what James Webb has added to this story. Because the connection between parent stability supernovae and the early universe is not just a chemical inference from ancient stars. Webb is beginning to observe the explosions themselves, or at least extraordinarily bright transient events in the early universe that are consistent with parent stability events. In May 2026, a paper published in the Open Journal of Astrophysics proposed that some of the unexpectedly bright early sources that Webb has been detecting, objects initially classified as extremely distant galaxies, might actually be parent stability supernovae. The argument is subtle and important. When Webb detects an extraordinarily bright, compact source at very high redshift, the default interpretation is that it is a galaxy, a collection of stars seen from an enormous distance. But a single parent stability supernova, at peak brightness, can briefly outshine its entire host galaxy. For an observer at Earth looking at a very high redshift event, the supernova and its host galaxy may be unresolvable. They appear as a single point of light. Some of the brightest early sources Webb has found objects that appeared to be extraordinarily luminous galaxies at redshifts corresponding to when the universe was only 200 to 400 million years old. Might not be galaxies at all. They might be the death flashes of individual parent stability supernovae from population 3 stars, caught at their peak luminosity. This is not a new idea. It was proposed as a theoretical possibility before Webb launched. But Webb's observations are providing the data needed to test it. By watching how these sources evolve in brightness over time, By tracking their light curves as Webb makes repeated observations of the same regions of sky, astronomers can distinguish between the steady glow of a galaxy and the transient flash of a supernova. Galaxies do not significantly change in brightness over weeks or months. Supernovae do. If some of the early bright sources Webb has found begin to fade, if their light curves show the characteristic rise and fall of a supernova rather than the steady luminosity of a galaxy, the interpretation will change. They will be reclassified as transients, as explosions rather than steady sources, and the pair instability interpretation will become more compelling. This monitoring program is underway. The results are still coming in. But the possibility that Webb is seeing directly the death flashes of population 3 stars, the first stars, destroying themselves in pair instability explosions in the first few hundred million years of the universe, is one of the most extraordinary possibilities in current observational astronomy. It would mean that the most violent stellar deaths in the universe are also among the first events that Webb can observe. That the earliest light in the universe includes, scattered among the first galaxies, the catastrophic self-destruction of individual stars of a type that no longer exists. The first generation of stars may have gone out screaming. Now let's think about what the chemical output of pair instability supernovae means for the universe we live in. Every heavy element in the periodic table above helium was produced by stellar nucleosynthesis. Carbon, oxygen, nitrogen, the elements of life, were forged in stellar cores and dispersed by stellar winds and supernova explosions. Iron, the most stable nucleus, the endpoint of nuclear burning, was produced predominantly in core collapse supernovae and thermonuclear supernovae involving white dwarfs. Gold, platinum, the heaviest elements, produced in the violent environments of neutron star mergers, where the extreme conditions allow neutron capture to build nuclei far heavier than iron can provide. Pair instability supernovae contributed to this cosmic chemistry in a specific and important way. Their ejecta is dominated by intermediate mass elements, oxygen, silicon, and the elements between them in enormous quantities. A single pair instability supernova ejects more oxygen than hundreds of conventional supernovae combined. More silicon, more of the building blocks of rock and silicate chemistry, the oxygen in your body, the silicon in the rocks beneath you, the sulfur in the chemistry of life. These elements were produced in stellar interiors and scattered by stellar explosions. Some significant fraction of these elements, particularly those scattered in the early universe, before the chemical evolution of the cosmos had proceeded far, were produced and dispersed by pair instability supernovae from the first generations of stars. The atoms that make you are, in part, the legacy of stars that left nothing behind. Stars that destroyed themselves so completely that no remnant survives, but whose atoms, scattered across the early universe, eventually found their way into gas clouds, into later stars, into planetary systems, into chemistry, into biology, into you. The most complete stellar deaths in the universe produced some of the atoms that make up its most complex products. There is something in that which deserves acknowledgement. Let's talk about why finding pair instability supernovae is so difficult and why SN 2023 VBW is significant despite not being a confirmed detection. The fundamental challenge is rarity. Pair instability supernovae require progenitor stars in the 130 to 260 solar mass range. These stars are rare in the present-day universe, perhaps 1 per million square light-years per century in a typical galaxy, or possibly less. In the Milky Way, such an event might occur once in tens of millions of years, or not at all, given the current metallicity of the interstellar medium. Finding these events requires observing many galaxies simultaneously, over many years, watching for the specific signatures that distinguish pair instability events from conventional supernovae. The signatures are not always clear-cut. The main distinguishing features are high luminosity, long duration, large ejecta mass, and absence of a compact remnant. But each of these can be mimicked to varying degrees by other types of events. High luminosity can be produced by conventional supernovae interacting with dense surrounding shells of previously ejected material. The interaction converts kinetic energy of the ejecta into radiation efficiently, producing luminosities comparable to pair instability events. These events are called interaction-powered supernovae, and they are the most common alternative explanation for apparently superluminous events. Long duration can be produced by very large nickel-56 masses. The radioactive nickel produced in thermonuclear supernovae decays with a specific half-life, powering the light curve of the supernova for months. A very massive conventional supernova producing a large nickel mass can have a long, slow light curve that superficially resembles a parent stability event. Large ejecta masses are harder to mimic but not impossible, and the absence of a compact remnant is extremely difficult to confirm observationally. A neutron star or black hole can be present but undetected if the surrounding nebula is not heated in specific ways. This is why the identification of parent stability supernovae has been contentious. Multiple candidates have been proposed over the past 2 decades. Some have held up to scrutiny, some have not. The community has been waiting for an event with a complete, internally consistent set of properties that matches the theoretical predictions in detail. SN 2023 VBW is the best case yet. Not perfect, not confirmed beyond all doubt, but the best case yet, an event where the ejecta mass, the light curve, the spectral properties, and the absence of remnant signatures all point in the same direction, with fewer alternative explanations available than for previous candidates. It may not be the final word. Science rarely has final words, but it is a significant advance in the ongoing effort to confirm that the rarest and most violent stellar deaths in the universe are real, not just theoretical predictions. Let's talk about what happens in the seconds and minutes after a parent stability supernova begins. The thermonuclear detonation that unbinds the star is essentially instantaneous on astronomical timescales. It spreads through the core at a significant fraction of the speed of sound in the degenerate nuclear matter, which is itself a substantial fraction of the speed of light. The detonation front traverses the entire core in a fraction of a second. In those fractions of a second, the nuclear burning that has been proceeding carefully over millions of years, fusing hydrogen to helium to carbon to oxygen to silicon, is replayed in reverse order at 1 billion times the rate in an explosive runaway that converts hundreds of solar masses of material into energy and new elements. The energy released in this detonation, 10 to the power of 44 to 10 to the power of 45 joules, is deposited into the stellar material faster than it can radiate away. The temperature spikes to billions of degrees. The pressure is extraordinary, beyond anything that exists in the interiors of ordinary stars by orders of magnitude. And then the shock wave begins. The shock wave propagates outward from the exploding core at thousands of kilometers per second, encountering the outer layers of the star, layers of silicon, oxygen, neon, helium, and finally hydrogen that were not involved in the nuclear detonation. These layers are swept up by the shock wave and accelerated outward. The shock wave reaches the surface of the star, a surface that, for a blue supergiant like the progenitor of SN 2023 VBW, is approximately 10 to 20 times the radius of the Sun, and reaches it in a matter of hours. When it does, the dense outer atmosphere of the star is accelerated almost instantaneously to velocities of 10 to 20,000 kilometers per second. This is shock breakout, the moment when the supernova shock wave reaches the stellar surface and the star's luminosity spikes dramatically as the compressed, heated surface radiates its accumulated energy. For a conventional supernova, shock breakout is a brief, often unobserved flash lasting minutes to hours. For a parent stability supernova, with its far larger progenitor and far more energetic shock wave, shock breakout is a more extended, more energetic event. In the minutes and hours after shock breakout, the expanding ejecta is extraordinarily luminous. The heated surface of the expanding cloud radiates intensely. For an observer nearby, within a few million light years, this would be the most spectacular visible event they could ever witness. A point of light brightening from stellar magnitude to something approaching the total luminosity of their host galaxy in the course of hours. At the distances of the supernovae we actually observe, millions to billions of light years, we see only a point of light brightening and fading over weeks and months as the light curve evolves. The physical scale of the explosion, the expanding cloud of material, the absence of a compact center, is inferred from the light, not directly observed. What we see is always the encoding of the physics in photons, always a translation, always a decoding, but the physics is as described. Fractions of a second of detonation, hours of shock traversal, the complete unraveling of a star that took millions of years to build. Now let's zoom out dramatically, beyond individual explosions, beyond individual stars. The universe, over its 13.8 billion year history, has produced an enormous number of supernovae. Estimates suggest that in the observable universe alone, roughly one supernova occurs every second, 1 per second, in one of the roughly 2 trillion galaxies scattered through the cosmic web. Most of these are conventional core collapse supernovae or thermonuclear supernovae. Parent stability events are a small fraction of the total, perhaps 1 in 1,000 or 1 in 10,000, depending on the epoch and the composition of the stellar populations involved. But even a small fraction of an enormous number is still a large number. Over the history of the universe, billions of parent stability supernovae have occurred, each one destroying a star entirely, each one releasing energies that dwarf anything else the universe produces outside of the largest black hole mergers, each one scattering hundreds of solar masses of material into the surrounding space. The cumulative chemical contribution of all these events, the oxygen, the silicon, the heavier elements scattered across billions of years and countless galaxies, is woven into the fabric of the chemical universe, into the compositions of galaxies, into the abundance patterns of ancient stars, into the availability of the materials needed for planets and chemistry and life. The universe's chemistry is, in part, the legacy of stars that left nothing behind. This is one of the stranger and more beautiful aspects of parent stability supernovae. The most complete destruction produces some of the most important construction. The stars that obliterate themselves contribute their material to the cosmos in a way that has persisted through billions of years of subsequent chemical evolution. Nothing lasts, but the effects of nothing lasting can endure for the age of the universe. Let's talk about what the next generation of telescopes will be able to do with parent stability supernovae, because the SN 2023 VBW detection is not the end of this story. It is the beginning. The Vera Rubin Observatory, now beginning full science operations in Chile, will survey the entire southern sky every few nights. Every supernova that occurs within its observing range will be detected, cataloged, and monitored. Over its 10-year survey lifetime, it will find millions of supernovae, an enormous statistical sample of stellar deaths across a huge range of galaxy types, redshifts, and environments. Within this enormous sample, parent stability supernovae will appear at a rate determined by how common the progenitor stars are in the local universe. Even if they occur in only 1 in 10,000 galaxies per century, Rubin's survey of millions of galaxies will find hundreds or thousands of them over a decade. With such a sample, the statistical properties of parent stability events, their light curve shapes, their luminosity distribution, their preference for specific types of host galaxies, can be measured with real precision. The theoretical models can be tested against a real population of events rather than a handful of individual candidates. The James Webb Space Telescope's contribution will be in identifying parent stability events in the early universe, the transient monitoring program that is already underway for the bright early sources that may be explosions rather than galaxies. As Webb continues to observe the same deep fields repeatedly, the light curves of these sources will reveal their nature. The Nancy Grace Roman Space Telescope, scheduled for launch in September 2026 and designed specifically for wide-field survey astronomy, will combine Hubble's image quality with a field of view 100 times larger. It will be able to monitor millions of galaxies simultaneously for transient events, including parent stability supernovae, at a rate and with a completeness that neither Webb nor Rubin can achieve alone. Roman is specifically designed to search for a type of event called a cosmological transient, a bright, short-lived event at extreme distances whose light curve and spectrum can be used to study both the event itself and the universe's expansion history. Parent stability supernovae, with their extraordinary luminosity, are detectable at cosmological distances, at redshifts of 2 or 3 or higher, corresponding to times when the universe was only a few billion years old. Roman surveys will extend the search for these events to the early universe in a systematic way that has not been possible before. The gravitational wave observatories LIGO, Virgo, and CAGRA, and their next-generation successors, have a specific sensitivity to parent stability supernovae through a different channel. While the parent stability explosion itself is not strongly asymmetric in the way that compact binary mergers are, the pulsational variant, the pulsational parent stability supernova, in which a very massive star undergoes repeated partial explosions before its final death, can produce gravitational wave signals. The repetitive mass ejections and pulsations of the massive star in the years before its final explosion might be detectable as a coherent gravitational wave signal if the event is close enough. No pulsational parent stability gravitational wave event has been detected, but the theoretical predictions exist, and the sensitivity of current and next-generation detectors is approaching the threshold where detection might become possible. The picture of parent stability supernovae that will emerge from the next decade of observations from Rubin, Roman, Webb, and the gravitational wave network will be incomparably more detailed than the picture we have today. The handful of current candidates will become a statistically meaningful sample. The chemical signatures in ancient stars will be connected to specific observed explosion properties. The population of early universe events will be quantified. And the theory, the physics of pair production and thermonuclear detonation in very massive stellar cores, will be tested against real observations rather than being constrained only by indirect evidence. The science is moving fast. The instruments are becoming sensitive enough. The detections are beginning to arrive. Let's return to the star itself, to the progenitor of SN 2023 VBW. Before it exploded, this star was one of the most massive and most luminous individual stars in its galaxy. Massive enough that a single star contained 170 to 350 or more times the mass of the Sun. Luminous enough at the extreme end of stellar luminosity that it emitted more radiation in a single second than the Sun will emit in months. It lived for a few million years, perhaps 3 million, perhaps 5 million. A short time by human standards and a cosmological instant by any other measure. In those few million years, it fused hydrogen to helium in its core, exhausting the hydrogen supply in perhaps 1 million years. Then it transitioned to helium burning, its core contracting and heating, its outer layers swelling. In its late stages, it burned heavier elements, carbon, neon, oxygen, silicon, in shells around a growing core of electron-positron pair-producing material. Through all of this, it was shedding mass. Very massive stars have powerful stellar winds, outflows of material driven off the surface by the intense radiation pressure. These winds can be so powerful that very massive stars lose a significant fraction of their initial mass over their lifetimes. A star that begins at 300 solar masses may have shed 50 or 100 solar masses by the time it reaches its final state. For SN 2023 VBW's progenitor, likely a blue supergiant in a low metallicity environment, the mass loss may have been less extreme than in a higher metallicity star, because the stellar winds are driven in part by the opacity of metal lines in the stellar atmosphere, and low metallicity stars have weaker metal line opacity and therefore weaker radiation-driven winds. This is why low metallicity environments are favorable for parent stability supernovae. Less mass loss during the stellar lifetime means more mass reaching the final state, increasing the probability of falling into the parent stability regime rather than collapsing conventionally to a black hole. The star burned. For a few million years, it burned with an intensity that made it one of the most luminous individual objects in its galaxy. And then the pair production began in its core. And then the detonation. And then nothing. 3 million years of stellar evolution, annihilated in a fraction of a second. Whatever was in the surrounding space, whatever molecular cloud material, whatever nascent planetary systems might have begun assembling around the star, was swept away by the expanding ejecta, dispersed by the radiation pressure of the explosion, irradiated by the intense ultraviolet and X-ray flux of the event. The neighborhood of a parent stability supernova is briefly the most hostile environment in the galaxy. And then, as the ejecta disperses and the radiation fades, it becomes just space again. Enriched space, filled with the products of the explosion. But space. Let's talk about what happens to the ejecta on longer timescales. The debris from SN 2023 VBW, that 170 to 350 solar masses of material, is currently expanding outward at thousands of kilometers per second. Every second, it occupies a slightly larger volume. Every year, its density drops as the same mass fills a larger and larger sphere. On a timescale of decades, the ejecta is still relatively compact, a cloud of gas and dust tens of light years across, still dense enough to be observable as a nebula in X-ray and optical wavelengths. The expanding shell of material, heated by the radioactive decay of nickel-56 to cobalt-56 to iron-56, glows as it disperses. On a timescale of thousands of years, the ejecta has expanded to hundreds of light years across. It is becoming a supernova remnant, a vast, thin shell of expanding material plowing through the surrounding interstellar medium. The collision between the fast-moving ejecta and the stationary interstellar gas produces shock waves, accelerates cosmic ray particles, and illuminates the surrounding region in radio, X-ray, and optical wavelengths. On a timescale of tens of thousands of years, the remnant has expanded to thousands of light years, and its density has dropped to the point where it begins to merge with the surrounding interstellar medium. The boundary between the remnant and the surrounding space becomes indistinct. On a timescale of millions of years, the material has mixed with the interstellar medium entirely. The chemical enrichment, the oxygen, silicon, and other products of the parent stability explosion has been incorporated into the surrounding gas, available as raw material for the formation of the next generation of stars. The star that left nothing behind has, eventually, contributed everything it was to the surrounding universe. Not as a compact remnant, not as a gravitational monument, but as chemistry, as enrichment, as the raw materials from which future complexity can be built. This is the parent stability supernova's legacy, not presence, contribution. A star that existed for a few million years, destroyed itself in a fraction of a second, and then spent the next million years slowly giving everything it was to the universe around it. Now let's make this personal, because there is a direct line between the parent stability supernovae of the early universe and the fact that you exist. The atoms in your body, particularly the lighter ones, the carbon and oxygen and nitrogen and sulfur that constitute the chemistry of life, were produced in stellar cores and scattered by stellar explosions. Some of them were produced in conventional supernovae, in the explosions of stars that left neutron stars and black holes behind. Some of them were produced in the winds of giant stars, shed gradually over thousands of years. Some of them were produced in binary systems where white dwarfs accreted material from companions and detonated in thermonuclear explosions. And some of them, a fraction impossible to determine precisely but almost certainly significant, were produced in parent stability supernovae. In the complete thermonuclear destruction of stars so massive that they left nothing behind. In the most violent stellar events in the universe's history, the oxygen in your lungs right now, the carbon in your DNA, the silicon in the rocks beneath your feet, some of that came from stars that ceased to exist entirely, that scattered themselves into the cosmos without leaving a trace of their former coherence. You are, in this specific sense, partially the product of the most complete destruction the universe produces. The atoms that make you up include atoms that were created in explosions so violent that the objects that created them no longer exist in any form. There is something strange and beautiful about that. The universe's most thorough acts of destruction have contributed to its most complex acts of construction. The violence is old. The complexity is new. And you are the complexity made partly from the products of the violence. Let's end with what parent stability supernovae tell us about the universe at its largest scale. The universe has a life cycle, not a single clean arc from beginning to end, but a complex, branching process of assembly and destruction, enrichment and dispersal, the building of complexity from simple beginnings and the eventual return of that complexity to simpler forms. Stars are the engines of this life cycle. They take the simple hydrogen and helium of the early universe and convert it, through nuclear burning, into the heavy elements that make complexity possible. They scatter those elements in their deaths. The scattered elements form new stars, new planets, new chemistry. The chemistry, given time and the right conditions, builds itself into molecules of extraordinary complexity, and those molecules eventually organize into structures that can reproduce and evolve. The parent stability supernova is an extreme participant in this life cycle, a star at the edge of what physics permits. More massive than typical, shorter lived than typical, more violent in its death than anything else, that contributes disproportionately to the chemical enrichment of the cosmos in a single catastrophic event. And then it is gone. No remnant, no marker, nothing at that location to say that something was once there and mattered and burned and contributed. Just the chemistry it left behind, dispersed through the surrounding space, eventually incorporated into what came next. This is, in a sense, a kind of immortality. Not the immortality of persistence, of being there, in some form, forever, but the immortality of contribution, of having built something into the structure of what followed so thoroughly that its effects persist long after its physical existence has ended. The parent stability stars of the early universe are gone. Every trace of their individual existence has dispersed and mixed and been reworked by billions of years of subsequent chemical evolution. There is no object in the sky tonight that is the remnant of the first parent stability supernova. But the elements those stars produced are still here, in the oldest metal-poor stars of the Milky Way's halo, in the chemistry of the interstellar medium, in the rocks beneath your feet, in the cells of your body. The most complete destruction the universe produces has left its mark everywhere. It just left it invisibly, encoded in chemistry rather than in the bright, dramatic presence of a surviving remnant. The stars that left nothing behind left everything. Sleep well. For those still listening, in the space between waking and sleep, my biggest goal on this channel is to reach 1,000 subscribers. If you enjoy falling asleep to my videos, please hit that subscribe button. We continue. There is a supernova happening somewhere in the universe right now. Not a parent stability event, those are rarer. Probably a conventional core collapse. A massive star somewhere in one of the 2 trillion galaxies of the observable universe, collapsing its iron core in fractions of a second, releasing a flood of neutrinos that will pass through everything in their path, producing a shockwave that will blow the outer layers into space and leave a neutron star or black hole at the center. This is happening approximately once per second. Right now, in this second, a star dying somewhere, and perhaps once per decade, per century. The timescale is uncertain, the events are rare. A parent stability supernova. A star at the extreme end of the mass distribution, somewhere in a low metallicity galaxy, triggering the catastrophic pair production in its core and detonating itself completely, leaving nothing, scattering itself into the cosmos. Right now, or in the very recent past by cosmological standards, the debris of SN 2023 VBW is expanding outward. 170 to 350 solar masses of material, moving at thousands of kilometers per second. The former star now a thinning cloud of gas and dust. Nothing at the center, just the cloud and the space it is expanding into. Somewhere in that expanding cloud are atoms of oxygen that were forged in the stellar core millions of years before the explosion. Atoms that have never been part of a planet, never been incorporated into chemistry, never been closer to a living thing than several million light years. Eventually, in millions or billions of years, those atoms will find their way into the interstellar medium of their host galaxy. They will be swept up in a gas cloud somewhere. The gas cloud will collapse. A new star will form. Perhaps it will have planets. Perhaps one of those planets will have the right conditions for liquid water and organic chemistry. Perhaps those atoms of oxygen will end up in the atmosphere of that planet, breathed by something that does not yet exist and cannot yet be imagined. The universe is patient. The distances are vast. The timescales are incomprehensible. But the atoms that came from a star that left nothing behind are still out there, still traveling, still waiting to become part of whatever comes next. As you drift towards sleep, somewhere in the universe, something is exploding. Something is leaving nothing behind. And the universe is, in its patient way, already beginning the long process of turning that nothing into something. Sleep well,